Thank you. Good morning. So the title of this talk is FPGA Microservices, ultra-low latency with off-the-shelf hardware. I'm going to talk a bit about what each of those words means. It's not very often that they get put together in the same sentence. I think when I proposed this talk, people thought maybe I was not for real. Like, are these tools too powerful for the job? Is this an appropriate use of technology? What does this mean, right? And I think part of it is that people have a lot of, people don't know what to do. And so that's really what I'm going to address today. I come from a trading company. Maybe that's what you think of when you think of a trading floor. That's a pit of lots of people shouting orders at each other. In reality, it's really more like this nowadays. Traders have the best LAN parties. And basically, what I really love about the trading environment is that there's nothing stopping you using whatever the best technology you can find is. If you can work out how to build something, and you can get a good strategy going and you can run it, then it should fund itself, so you don't have to worry about grants and customers and clients and things like that. In some sense, it's a pretty good driver for research and innovation. And when there's things like FPGAs, we're in this environment where you really need to change the code really, really quickly. So if someone else comes up with a new strategy or something, you need to be able to react to that and you change what you're doing. You are generally not allowed to have systems that crash, so you really, really need to minimize bugs. Some exchanges will actually kick you off. You can not be allowed to trade anymore if you lose connectivity, which means that you might pretend that you might not have got an acknowledgement or might not have seen some order in the market. So you really need to be connected, and you've got this agreement with the exchange that you're always connected. So having a really high reliability environment where you just don't crash is pretty important. Now contrast that with FPGA programming, which traditionally has very, very long development cycles, like we're talking months, even years, to build hardware products. It makes it very difficult to react and put in a new way of operating the next day. Now the title of this talk is FPGA Microservices on off-the-shelf hardware. So I was going to discuss some PCI card solutions, which if you have a data center, you can put a card into a network server, and it will actually take over the network connection. I'll go into that a bit, but what's really exciting, yesterday this article came out that Amazon AWS is launching FPGA instances. Now these use Xilinx FPGAs, and they allow general purpose applications that you can build. If you can build FPGA software, you can put it onto the cloud. So that will get rid of a whole lot of deployment issues of actually having to set up your own servers, having to maintain them, and so on. Just the usual kinds of cloud benefits. No need to source your own components to find what you're going to run on. So you'd actually be able to, this is just a screenshot of the dev instance that you can actually log in. Just have a normal cloud instance, but you put a binary onto it, which will then run on the FPGA. Just discussing microservices, why we talk about microservices here. The usual sort of, there's a lot of discussion of what microservices are and why it'd be useful, but for the point of view of putting things on an FPGA, what I really like about the architecture of building larger systems with small services is that it allows you to compartmentalize concerns. That means that you can scale separately. So if you have one part of your application which is doing authorization, for example, another one which is doing some computation, then you can put them onto different machines, different hardware solutions in different locations, depending on what they're doing. So for example, if you have something which needs to connect to databases, well, you might want to run that on a CPU. If you have something which is doing some machine learning, perhaps that'll go on a GPU. If you're doing something which is purely calculation-based and you want to be able to get a very fast response, then perhaps an FPGA is a plausible solution for that. What do I mean by ultra-low latency? Now, if you're doing a video service, then you need to be able to respond within like 30, 60 frames a second, which gives you some number of milliseconds that you need to be able to do a calculation in. We're getting towards some really interesting applications with virtual reality now. VR optics actually require you to have much higher frame rates, so you get more of a sense of dissonance if you have even just like 30 frames a second, which is fine for a still image over here. When you're immersed in that, then you actually notice flickering much more. Becomes quite disturbing. And haptics is where you're actually having a touch sense, and the human touch sense is much, much more sensitive than our optical sense. And so you actually need refresh rates up to thousands of frames a second, of updates per second. Now you translate this into latencies, and suddenly you're talking sub-millisecond latencies for responses. So my favorite example of why this would matter for a microservice is imagine that I'm building like a virtual world where you want to be able to walk around in. People in different countries are connecting to each other, are talking to each other, are in the same world, moving objects around, throwing a ball or something. You want to be able to have simultaneous updates between multiple participants. Now, if you have a traditional microservice where you have this sort of ping pong between multiple servers that are coordinating the behaviors of these people, so locations, other objects in the room from multiple parts around the world, each hop adds a little bit of latency. So if you have even like a millisecond of latency at each hop, then pretty soon it'll add up to something that's worse than the frame rate that you want. When you start talking about haptics and actually having to deal with object collisions and finding out when something hits somebody and get that sense immediately, then even that's not fast enough. So we're really talking about every microsecond counting in that kind of environment. So I'm just going to talk about what an FPGA is. How many people here have actually worked with FPGA hardware? There are a small number, a few, not so many. So basically from our point of view, it's a separate chip, okay? It could exist on a network card, it could exist, there are some new ones which are together, a system on chip with a CPU and so on. It could just be on the cloud somewhere, it's an FPGA now. But basically what it is, programming-wise, it's a bunch of logic gates, so lots and lots of little lookup tables that can be programmed in the field, which means that you can change what they're doing. You load a binary onto it, and that will describe the configuration of all these gates, how they all hook up, how they connect to each other. From a programmer's point of view, it's just a build target. So you generate a binary file, you use an application like Vivado as a commercial one, you write source code in a language like VHDL or Verilog, and basically you're just writing text files, you're building stuff. So we're back in software land now, we've got a programming language, we can compile that down to a binary, flash it, maybe reboot, and you've got an execution happening on hardware. So it is a pretty normal kind of building environment nowadays. I'll even go as far now as saying that I'm really treating VHDL and Verilog as intermediate languages. Generally don't need to hack them too much directly. VHDL itself, though, it's pretty tedious to develop, right? So it's more low level than assembly. You're describing circuits of logic gates, you're thinking about ands and ors and things. You're worrying about clock timings. You're actually building a pipeline, so you're making up how different stages of the circuit are going to, how they're going to operate. You have to make sure that each one only has a certain path length to meet the timing of the clock that you're setting up. If they get too long, then you put a register in between, and that delays the pipeline by one more clock cycle. So you actually build up sets of logic, and each one, you can imagine, you can have as much parallel going on parallel paths as you wish, as long as the whole thing fits within the die, within the number of gates that you've got in the FPGA, and that is growing really, really large now. But you are missing out on stuff. You don't necessarily have things like floating point numbers. You can get libraries that will give you floating point support, but you generally have to work in much more low-level math operations. And sometimes the tools can be a bit flaky. So they've been around for a long time. They are getting better and better all the time, of course, but maybe it's not as mature as some of the software build chain. But on the flip side, it's possible to create really, really efficient circuits. So you can optimize, you can use as few bits as you want. So I'll do things where I'm having like 17 bits here and 6 bits here, doing a lot of fixed point math and things like that. And you can optimize for time by doing more things in parallel. So you can just set up, right, I want to do like multiple copies of the same object. I mean, of the same computation. For example, when you do a for loop in VHDL, then you actually end up with multiple copies. So it's a completely different way of thinking to normal sequential programming. It can be very tempting, it can be very easy to build huge circuits without really realizing what you're doing if you think in terms of sequential coding. So, what do we do when we've got something that's really hard to do and we want to get some reliable software out? Bang, go straight to Haskell. So I'm using this language called Clash. It's pretty much Haskell. It's got some extra features which are more like library, or a different prelude, which is the basic library that you use in Haskell. It's got types like length typed bit vectors, and so that means that the number of bits is actually part of the type. So you've got natural numbers in the type signature. So if I make like a 17-bit signed integer, then that's a 17-bit signed integer. It's got some primitive data flow strategies, like Billion More machines, which I'll talk about, and parallel reducers. So what this means is that you can set up computations and it will actually build a circuit which most efficiently implements the idea of the computation. So for example, if you're folding addition over a vector, now in Haskell, fold is it's a function which you generally might apply to a list, and it will take the first element of the list, maybe take the first two elements, add them together, then get the next one, add that, next one, add that. And that's when you fold addition across a list. That's a way to describe that you want to do a computation over a collection. That's the kind of thing that in like C or Java or something you would generally write a for loop for. You say, for iterating over these elements, then add up a temporary variable. But there, if you're doing that, then you're explicitly saying how you want to do the computation. In Haskell, what you're really describing is, I want to do this computation. I just want the general concept of adding up all the numbers in this vector. On a CPU, sure, that will go through and add them up one by one. But in hardware, you can make parallel things, so you can split the task up. So when you do that in Clash, you'll actually end up with a network like that, where lots of pairs are put together, added in parallel. So like each level here is going to be a different pipeline stage. May be a different pipeline stage. But the dependencies are wired up like that, so that, say you have your log n tree of adders rather than a order n set of additions. And if we go back, that was the code, was just fold plus over the vector. So it's very, very, very terse to write. And you end up with really, really more complex and neat hardware. There is some poor support, they say, for recursive functions, because you can imagine if you are recursing, then you're actually going to get infinite paths of hardware. So you need to limit that and understand what you're doing when you want to do things, or when you actually want to do stuff over and over again. But other than that, most of Haskell is supported. So just in general, I think Haskell is very well suited to designing parallel systems because the language describes the dependencies between expressions. You're actually just setting up expressions in terms of how they're built up from other expressions, and that translates pretty directly into the hardware. So quite often I'll have a function with a where clause which defines smaller expressions which I'm going to refer to in the main expression in the main function. Each of those can then turn into a separate pipeline stage pretty easily just by putting a register keyword around them. So for a quick example, I'm just going to go through CRC32, which is a pure math thing. So let's say we just got a little checksumming server. It's going to be 32 lines of Haskell, so really short. It's got 2 one-liners for testing. So we're actually going to build a small test bench. Now Clash here generates 11 files of VHDL. And that includes 5 files for a test bench, which normally you'd have to write by hand. Normally that can be very, very tedious. So what happens? People skip it. Then what I'll go through here is loading that into YOW, which is a commercial tool for generating the circuit so we can see what it looks like and synthesize it to make an actual optimal circuit layout. What we end up with is a really, so this is all from generated code basically. In the hardware simulator, we actually get a Boolean done signal. It switches to true when we know the test passes. So we actually get a waveform view. It's all cool. We generate some test data. So because I want to be able to compare this to some known good data, I'll start off with a standard C implementation of the CRC32 function. We build that, run it on a string. We end up with some integers. So that's going to be the expected output that we will use later for our testing. And that's generated from C, from something that we know is implemented correctly. Small thing here, we've just added in a 0 byte at the start of the input, which I'll use for because the circuit starts off in 0 state. But yeah, that's all the C code. We set this up into when we build the hardware, we set up a thing called a mealy machine, which is just simply a component that has an input and output and maintains a state. So it's a general hardware design thing, but in Clash we actually have a mealy function. So we can pass in a transform function, which is the CRC32T transform. On the bottom line, we just pass that into the mealy with an initial value of 0. And that gives us our whole CRC32 mealy machine function. So one thing we'll notice here is the bottom function, CRC32, once it's gone into the mealy machine, it's actually of type signal. So it's got an unsigned 8, which is, of course, an 8-bit unsigned integer as input, and it's outputting an unsigned 32. Each of those is wrapped inside a signal, which means that this is going to continuously operate as something that changes what's happening on a wire. Whereas the CRC32T function above that is not a signal function. It's just a pure mathematical function of taking an unsigned 32-bit, an 8-bit, and outputting a tuple of 2 32-bit integers. So there's no signals going on there, and that's just that's a straight Haskell function using these Clash types, which give you the bit lengths. One thing that's really cool is the truncate B function there. So we'll see, if we look a bit closer into that step function, on the third line from the bottom, it's got a truncate B in there. And what that actually does, it simply truncates to bit values. So here we might take a 32-bit value down to an 8-bit value. The type of that is unsigned A to unsigned B, which means it's polymorphic, and Clash will actually generate whatever you need to change the size of integers, which means that it's actually going to remove wires. There's also a resize function which can add 0 values. And because that's all inferred by the Haskell compiler, you don't need to specify what the input and output bit widths are or anything like that, because that's all encoded in the type already. So it actually ends up that you have to write a lot less code and you have to think less about the details of the hardware that you're designing than you would if you were developing the VHDL directly. Okay, so we have a CRC32 table in here, which is just a big ROM table that we're going to load, that we're going to have on the FPGA somehow. I'll get into that later. We implement that as an async ROM. In Clash, that means we just say async ROM file of size 256. And we give an input data file, which the compiler is going to read at compile time, and it's going to generate that as part of the binary. And finally, we end up with we build a top entity. Now, the top entity we're going to use is just the CRC32 signal function. So any signal is part of a synchronous, a clocked circuit. One really cool thing you can do is then compose Mealy machines. So you have, that's just one way of describing one. You could use that as one pipeline stage, and then you can compose those together to make larger stages as well. And finally, the test bench. So this is where we're really starting to do things that we can't normally do easily in VHDL. So we specify our inputs, which here we start off with 0, just to have nothing in the circuit to start with, and 79, 112, whatever, are the ASCII letters for Optiver, and then the expected output is what our C program produced earlier. And so we can just specify those with the Clash functions for the stimuli generator and the output verifier, and that'll then generate a circuit which in simulation will have a stimuli generator will actually be a little bit of the circuit that generates those numbers, and the output verifier will look at those and check if that's what we were expecting and put out a Boolean signal, which is the done value and the true signal at the end. But before we do that, we can do something which we can't do normally with VHDL, is that we can test this in a software interpreter. So we run Clash Interactive, which is really just wrap around GHCI, the standard Haskell interpreter, and we can sample that expected output of top entity test input, which is running the main function. It does actually it gives you the whole signal, which is all false, 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 and then there will be a true at the end. With this caveat of what I copied out here from the docs. Finally, if we're happy that that works, and we will get the true, we can just generate VHDL. Recently, I've also been generating Verilog, similar kind of thing. You can just do :Verilog or /-Verilog in a makefile. And yeah, as I said before, I'm basically treating VHDL or Verilog as intermediate languages. They're just generated by Clash. Generally, I don't need to do anything. I just load them into Vivado and build. Yeah, I did find one compiler bug with Clash last week where it was, I was doing some fixed point math, and it was generating an argument. It was giving an argument literal, which was like 132 bits or something, and trying to put that into a 127-bit argument. And because it was giving it in hex, it couldn't do 127 bits. So that was really, I had to do a manual truncate in the generated VHDL. That's about the only time I've really had to go in and hack the VHDL directly and change it. Generally, it just works as, you know, as an intermediate language. So that's a pretty big change, like not having to think about thousands and thousands of lines of VHDL. So run simulation, test passed. We have a system clock, we have the 8-bit input, and we have the 32-bit output as the numbers at the bottom. But the main thing is we can see the true signal at the top when it's finished. After we've done that, so we know that it simulates okay, that the circuit should do what we want, we make an elaborated design. So that's how all the logic fits together. So here we can see all the adders as an actual circuit that it would be developing, but that's still just logical components. What we then do is synthesize it, so this then goes down to the actual gate design in the FPGA. So we can see in the very top corner, we've got the 8-bit input and 32 bits, 32 lines of output at the other end. All these little yellow boxes in the middle are all the LUTs, the lookup tables, which have been generated, and they're just binary values. They might have like 3 Boolean inputs and 1 Boolean output or something like that. Multiple ones, so yes, in this design, some of them are 2 or 3 bits in, some of them are 6. And literally, what Vivado has done is work out what the optimal way of implementing all those logic gates using these lookup tables could be. And this is, remember, this is like for 8 bits of input coming in. So it splits them all up. So once you get down to this level, then it's pretty hard to follow what's actually going on. You can look at each of those tables, and each of those LUTs has a different binary lookup table which has been generated. Now you remember that we had a ROM. We had a big ROM file of CRC values that we were meant to load in somewhere, and I can't see any big ROM anywhere. So what's actually happened? The FPGA does have block RAM, so sometimes if you've got large data, it will be stored in RAM, which there can be blocks situated throughout the chip. But for this small function, Vivado worked out that it could actually implement it as a bunch of different lookup tables. So the data lookup is actually spread across all these LUTs as well. So yeah, there's no way you're going to go backwards from the synthesized design to the logical circuit to work out what's actually going on once you've implemented it like that. So that's pretty complex. How can you remain agile when you end up with systems like that, and when it can be really hard to test eventually? Like, you're going to have to put this onto hardware at some point. You're going to have to load it and run it. So yeah, with normal VHDL design, if it takes 6 months to develop a moderately sized application, then yeah, it's very hard to remain agile. And remember, like for the trading environment, the requirements keep changing. You need to be able to develop systems really quickly. So I'm not even talking about bug fixes here. Like, we've got to move on from software having bugs. We need to actually get new, better features out. So what's really good with Haskell and Clash here is just the general idea that if it compiles, it works. Now I know, people think, nah, it can't really be real, but that is really my experience with Haskell in general. With Clash, you do have this extra layer of putting it into hardware, these extra steps, then it has to meet timing. If it doesn't meet timing, you go back and generally just add registers, split up your pipeline stages and so on. Which again is very easy because the code has already specified you've logically separated the different parts of each function, so it's quite easy to go through and add registers to it later. The fact that you can run tests in the software interpreter before you've generated VHDL, that means that you can set up build bots which will test out the code whenever you push changes without requiring having FPGA hardware or all the commercial tools on every build bot. So you can just set up a standard, whatever CentOS environment or something, and install Clash on it and run any tests. So it just becomes another part of your normal software deployment setup. So going to conclude there. The really interesting thing here is that FPGAs are becoming commonly available. What I really wanted to get through is that this is not some crazy thing that only really specialized applications are using. I mean, it is now, but in the future there's no reason that you can't deploy this for common applications. And as we have low latency requirements in more areas, things like virtual reality, and we can get FPGAs on cloud services. We can deploy them much more easily. I think this is a way this is going to become more and more common. And really, there's no need to fear this whole long development cycle. Using tools like Haskell and Clash, you can actually build it up as part of your normal software. You can build source, test, deploy, get a binary out there, have it as your normal continuous integration, continuous development, continuous deployment, and yeah, and remain agile even though you're building on FPGAs. Okay, I'm going to finish up there. Thank you.